Good afternoon, students. Welcome to our teleconference live program on low temperature physics and applications of low temperatures. So, I am Dr. Vijaya Ushasree, Assistant Professor, Department of Physics, Dr. Ambedkar Open University. సో మనతో పాటు ఈ లైవ్ షో అనేది మనకు తెలుగు ఇంగ్లీష్ మీడియం రెండు మీడియాలలో జరుగుతుందండి. సో మనతో పాటు ఇక్కడ మన స్టూడియోకి వచ్చినటువంటి ఇద్దరు ఎక్స్పర్ట్స్ ఉన్నారు, వాళ్ళని కూడా పరిచయం చేసుకుందాం. ఫస్ట్ ఆఫ్ ఆల్ ఐ ఇంట్రడ్యూస్ చందన, డాక్టర్ చందన. షీ ఈజ్ అసోసియేట్ ప్రొఫెసర్, డిపార్ట్మెంట్ ఆఫ్ ఫిజిక్స్, గవర్నమెంట్ డిగ్రీ కాలేజ్, మహేశ్వరం. అండ్ ఇంకొక ఎక్స్పర్ట్ ఉన్నారండి, డాక్టర్ సిహెచ్ వరలక్ష్మి గారు, and she is also assistant professor, department of physics, government degree college for women, and Sangareddy. So we ఈ కార్యక్రమం మనకు మొత్తము 1 గంట పాటు ఉంటుందంటే, అంటే 60 నిమిషాలు ఉంటుంది. ఈ 60 నిమిషాలలో 50 నిమిషాలు మన ఎక్స్పర్ట్స్ ఈనాటి మన లో టెంపరేచర్ ఫిజిక్స్ అండ్ అప్లికేషన్స్ ఆఫ్ లో టెంపరేచర్ గురించి డిస్కషన్ జరుగుతుంది, ఎక్స్ప్లెయిన్ చేస్తారు. సో దాని గురించి మీరు ఈ కార్యక్రమం లాస్ట్ చివరలో మీకు ఏమన్నా డౌట్లు అనేటివి ఉంటే కనుక యూ హ్యావ్ టు ఎక్స్ప్రెస్ యువర్ డౌట్స్ విత్ అవర్ ఎక్స్పర్ట్స్. దాని గురించి మీరు మాకు ఫోన్ చేయాల్సిన నంబర్లు ఒకసారి నోట్ చేసుకోండి. 04023680456. మళ్ళీ ఒకసారి చెప్తున్నానండి, 04023680456. ఈ నంబర్కి మీరు ఫోన్ చేసి మీ యొక్క ఏమన్నా డౌట్ ఉంటే అది మీరు నివృత్తి చేసుకోవాల్సిందిగా కోరుచున్నాము. ఇంకొకటి ఏంటంటే గమనిక, మీరు అడగవలసినటువంటి ప్రశ్నలు, వాట్ ఎవర్ యూ వాంట్ టు ఆస్క్ ద క్వశ్చన్స్ విత్ అవర్ ఎక్స్పర్ట్స్, ఈనాటి కార్యక్రమం భాగమైనటువంటి లో టెంపరేచర్ ఫిజిక్స్ అండ్ అప్లికేషన్స్ ఆఫ్ లో టెంపరేచర్ మీద మాత్రమే అడగవాలనని కోరుతున్నామనండి. సో ఇక్కడ ఫస్ట్ ఆఫ్ ఆల్ అసలు లో టెంపరేచర్ అంటే ఏంటి అనేది మనకు తెలియాలండి. సో ఈ లో టెంపరేచర్ అంటే ఏంటి అని అంటే, ది లో టెంపరేచర్ ద స్టడీ ఆఫ్ ద బిహేవియర్ ఆఫ్ మ్యాటర్ నియర్ అబ్సల్యూట్ లో టెంపరేచర్, వెరీ లో టెంపరేచర్, దట్ ఈస్ కాల్డ్ ద లో టెంపరేచర్. సో ఈనాటి కార్యక్రమైనటువంటి ఈ కార్యక్రమంలో మనము ఏవేవి మనము డిస్కస్ చేయబోతున్నాము అని అంటే, ఒకటి ఇంట్రడక్షన్, లో టెంపరేచర్ అంటే ఏంటి, లిక్విఫికేషన్ ఆఫ్ హీలియం అండ్ జౌల్ కెల్విన్ అండ్ జౌల్ థామ్సన్, వీటన్నిటి గురించి మనం డిస్కస్ చేయబోతున్నాము మన విత్ ఎక్స్పర్ట్స్ తో. అదేవిధంగా అప్లికేషన్స్ ఆఫ్ లో టెంపరేచర్ కూడా మనము మాట్లాడుతున్నామండి ఈనాటి కార్యక్రమంలో. సో నేను ముందుగా మన ఎక్స్పర్ట్ అయినటువంటి డాక్టర్ చందన మ్యామ్ ని అడుగుతున్నానండి. చందన మేడం, అసలు లో టెంపరేచర్ అంటే ఏంటండి? వాట్ ఈస్ మీన్ దట్ లో టెంపరేచర్? వాట్ ఆర్ ద ఎక్స్పెరిమెంట్స్ ఇన్ దట్ లో టెంపరేచర్? ప్లీజ్ ఎక్స్ప్లెయిన్ టు అవర్ స్టూడెంట్స్.
Definitely. First of all, I heartfully thank Dr. B.R. Ambedkar Open University, Department of Physics, for giving us this wonderful opportunity. And dear all students, today we are there here actually to explain you the different concepts of coming under low temperature physics and the experiments which we take up in our UG syllabus as well as they are used in your PG, in your coming PG. And also the applications will be explained by my colleague Dr. Varalakshmi madam. Now let me go into my concept. So my lecture will be of containing the introduction and methods of attaining low temperatures and Joule Kelvin effect, then also behavior of gases at different temperatures and expression for Joule Thomson cooling and liquefaction of helium Kapitza method, and also the adiabatic demagnetization. So I'll just go through all the things and I'll explain in detail the experiments. So if you have any doubt, you can easily clarify through the phone number which was provided by our Dr. Usha madam. Next, coming to the next slide, why? So why we need to know about the low temperatures? Actually, madam has given a detailed definition of low temperature, but still why we need to know about low temperature? Enduku telusukovali? What is the application, main use of the low temperature? As we every day go through our home, everyone in their house we have a refrigerator, right? So we preserve our vegetables, any other matter suppose, which has to be prevented from interacting with the outer atmosphere, like antibacterial activity. So in order to prevent the food materials not to get succumb to the bacteria, we use a refrigerator in our homes, and every place we use that. So for food safety, as you are able to visualize in the screen, for food safety purpose, preventing food spoilage and potential food poisoning, and also preservation of quality. So the quality of food will be the same. So if you preserve some other food like vegetables, the quality will remain the same for few days, right? At least for few days. So for this, by achieving this purpose, we use the concept of low temperature. And also for the medical applications. So for cryotherapy and other, in order to prevent the blood storage, damage of the blood storage, which we put the blood storage for blood banking purpose and all. Then also for industrial applications, we have wide applications of physics in industrial applications, because superconducting materials, we use this low temperature physics, liquid helium, where we run the magnetic levitated trains. So they are called maglevs. So all these things were comes under extreme low temperature conditions, right? So let us learn some of the processes where we attain the low temperatures. Okay, so let us go beyond that. So let me give a brief introduction. Actually, we all have the psychology, like every person, what is the low temperature you see everyday life? So everyone says that it's 0 degrees centigrade, right? Whenever you see the ice cube, so whatever, any child, any small child, what does he answer? He or she will answer, what is the lowest temperature you have experienced in your lifetime? So they say that it's an ice cube, right? So the similar fashion was there with the scientists in the previous years. Then later Fahrenheit, you know that Fahrenheit has come into the picture, and he has told that when a common salt or potassium hydroxide is mixed, then we can have some more low temperatures than 0 degrees centigrade. Okay, so he has found out the temperature to be minus 18 degrees centigrade. By common salt and ice, when we mix up, we get a lowest temperature than that of 0 degrees centigrade. Then later Fahrenheit has constructed a thermometer where the lowest temperature has reached to minus 22 degrees centigrade. Okay, then we have let me go to the methods of attaining low temperatures. So we have different methods to attain the low temperatures, but in particular the 4 primary important methods which we are going to deal today. I just want to go with a glance on that. Later we will go in the detail while I am explaining the experiments which are related to 2 of the methods which I am going to talk about. Okay, so first of all we will see the evaporation of liquids under reduced pressure. Okay, actually our ammonia, when you take the ammonia, liquid ammonia, so ammonia can be liquefied without any other temperature conditions. At any temperature, normal temperature condition, by applying pressure, high pressure, we can attain the liquid form of ammonia. But when you come to other gases like hydrogen, nitrogen, helium, oxygen, for them we need to apply pressure below some temperature, below a certain temperature. So what is the temperature called? Critical temperature. So the temperature below which, if you apply some pressure in the range belonging to that type of kind of material which we are talking about, which gas we are talking about, based on that, by applying the pressure below the critical temperature, we obtain the liquid form of oxygen or nitrogen or hydrogen. So if you can see on the screen now that ammonia for 135 degrees centigrade and sulfur dioxide 158 can be liquefied by applying pressure only. There is no condition for the temperature, but the temperature condition comes for the oxygen, nitrogen and helium and hydrogen. So you can see there clearly that hydrogen, it is liquefied only at minus 240 degrees centigrade, and helium it is at minus 268 degrees centigrade, right? Next, the second process which we see usually is cascade process. So you know what is a cascade meaning? It's a continuous repetition of the process which we do that, right? See, if I do one process and I attain a temperature of minus some 290 degrees centigrade, then again I have to go back, I have to put the gas again in the same process and attain the lowest temperature than that of minus 290. So we can achieve this by doing the series of processes. So that series of processes is called cascade process. Okay, so the lower boiling points of liquid at that position of the liquid has been taken, and it is continuously cycled so that we will attain our lowest temperature. This process was developed by Pickett, and Cameron Owens have done the liquefaction of oxygen using this method. Okay, you can find out so much literature is available in the web, students, so you can just browse it off and attain the knowledge of this process. Okay, next comes Joule Kelvin expansion coupled with regenerative cooling. So this Joule Kelvin expansion with this the porous plug experiment we'll explain in the coming slides. So this experiment where we have found out that hydrogen and helium gases can be liquefied at minus 240 degrees centigrade for hydrogen and helium minus 268 degrees centigrade at 1 atmospheric pressure, students. So the pressure is always has to be considered while talking about the attaining the low temperatures. When we come for adiabatic demagnetization, so this is one of the most important concepts, methods in attaining low temperatures, because the Joule-Thomson effect or Joule Kelvin effect have failed in producing a temperature below 1 Kelvin. But later, using this process, two of the famous scientists have given this adiabatic demagnetization. So we take a paramagnetic salt or paramagnetic substance we call, which is magnetized already, and then we just demagnetize the paramagnetic salt in some pressure conditions, in the particular pressure and temperature conditions. So by that we can achieve a lowest temperature of 0.0014 Kelvin. Okay. So these are all the 4 methods which we have summarized, madam. Yeah. Then you're just talking about the procedures which I need to explain. Okay.
మనకు ఇప్పుడు సిస్టమ్స్ 3 సిస్టమ్స్ అని అంటున్నారు కదా, యాక్చువల్లీ వాట్ ఆర్ దట్ సిస్టమ్స్? ఫస్ట్ ఆఫ్ ఆల్ వీ హ్యావ్ టు నో అబౌట్ దట్ 3 systems we have, I think so. Yeah, that so we can discuss thermodynamics system. Okay. Yeah, in thermodynamics.
Okay. So dear students, actually we are talking about thermal physics, right? So thermal physics itself is a wide branch of physics where we deal everything regarding the temperature and heat energy exchange and heat energy to conversion of heat energy into mechanical work, or one vice versa, like mechanical work into heat energy. So there we particularly talk about system and surroundings. So in a particular system, a thermodynamic system, where it is an enclosure, a thermodynamic system. Yeah. So systems are classified into 3 types, yes, as madam is asking to explain them in detail. So we have 3 types of systems: a closed system, an open system, and an isolated system. Okay. So the types of the system, these 3 classifications were depending upon the exchange of matter and energy between the system and the surroundings.
Yes.
So we know that there is always a scope of exchange of heat energy and matter between the system and the surroundings. So based on this concept, we have broadly classified them into 3 systems. So coming up to the closed system. In a closed system, there is no chance of heat exchange, neither heat exchange nor matter between the system and the surroundings. So such type of system is called a closed system.
And what
then we come
system?
to isolated system. Okay, isolated system, we have neither heat energy nor matter. When we come to closed system, only energy is exchanged, no matter. When we come to open system, both energy and matter will be exchanged between the system and the surroundings. So we have 3 types of systems in this way.
Okay. Chandana, can you tell that which system comes under this Joule Kelvin effect? Can you explain that?
Yes, madam. So now coming into the deeply into the Joule Kelvin effect and porous plug experiment. So here we have an isolated system here, where all the where the entire gas is when entire gas is going to undergo.
Continue.
Okay. So we have a brief diagram representing on the screen now. AB is a thermally insulated cylinder which contains a porous plug G, where you see the porous material in between G here, diagram G here, and the highest pressure is on the left hand side P1, while the right hand side the pressure is denoted as P2, where C and D are the non-conducting pistons, as you are observing on the screen now. Whenever a gas is made to pass from left hand side to the right hand side, that is the high pressure region to the low pressure region, then the change in the temperature occurs. While they are passing through the region, they are passing through what kind of material? that is a porous material, that may be a cotton or wool, where it is very much supportive for the gas to pass through on. Okay, so then there is a change in temperature which happens inside this experimental system. So this kind of process is called Joule Kelvin effect. Next, the entire process can be explained by using this equipment. So you see that we have a porous plug here, which is G here. You can see here on the screen now in this diagram, the experimental setup this is. So this equipment consists of a cylinder, a cylindrical tube. You can see here this one, the cylindrical tube, it is written here, the cylindrical tube, which is a non-conducting one, because we need not have any conduction possible there. And there you have two platinum resistance thermometers which were designated as T1 and T2 here, and two Ds are visible here. Students, are you able to see that? So two Ds are there. So what are those Ds? They are perforated brass discs. So perforated means with some holes. Okay, so two discs which are of the shape of discs. You imagine discs means a circular shape. So two discs are kept on the porous material G. Okay, they were just tightly closing that porous material. So then you have two on the right side and left side, you can see that they are just packing off the entire porous plug tightly. So there is no exchange of heat between the systems and the surroundings. That is the main concept to achieve that we have packed like that. So the two jackets are there on the both sides. The jacket is always packed with the felt. Felt means it's also a material like silk threads and wool. Okay, and also it may be an asbestos material. Now what happens? Let us see that. So you can see, students, here's S. S is the spiral. Okay, I'm sorry. S is the spiral tube here, which is extended towards the compression pump P. Okay. Now what happens? Now we'll put the gas here. So let me put the helium gas here. Okay. And now we'll compress the pump. So we'll move the pump little bit inward. That means we are compressing the pump here. So we are increasing the pressure here. So obviously the gas will pass through this spiral tube. While it is passing through the spiral cylindrical tube, what happens is it is kept in a water bath, right? You are seeing there, this is the water bath W. So what happens? Because of the water, the temperature of the helium gas that was at this compression, which attained some temperature because of the increase in the pressure, will get reduced because of the water bath. The pressure పెరుగుతుంది కదా, ఎందుకు కంప్రెషన్ చేస్తే ప్రెషర్ పెరుగుతుంది గ్యాస్ కి, ఎక్స్పాన్షన్ అంటే ప్రెషర్ తగ్గుతుంది. It's a basic principle in thermodynamics. So here we are doing the compression ante emaitadi, the pressure will build up in the gas in the cylinder piston. So what happens? A pressure ekku unna gas anedi lopaliki veltundante temperature kuda perigindi. You want to reduce the temperature. Mana primary agenda enti? We want to get low temperatures. Kabatti takku temperature kavali ante we'll pass that through the cylinder. While we are passing through the cylindrical tube, అక్కడ ఏమైతుంది, వాటర్ ఉండడం వల్ల వాటర్ లోకి హీట్ అనేది ఎక్స్చేంజ్ అవుతుంది. సో ద టెంపరేచర్ ఆబ్వియస్లీ డిక్రీజెస్. దెన్ దట్ డిక్రీజ్డ్ టెంపరేచర్ ఉన్న గ్యాస్ విల్ పాస్ త్రూ దిస్ perforated glass tubes, that D and D, perforated brass discs, where you will see the porous plug there G, right? So అప్పుడు వెళ్ళినప్పుడు what happens when obviously by Joule Kelvin effect మనకి ఏం చెప్తుంది, whenever a gas passes from that high pressure, constant high pressure region to a constant through porous plug to a constant low pressure region, there is a change in temperature. So obviously the gas comes out of this perforated brass discs, and then the temperature will be measured by platinum resistance thermometers. So we can obtain liquefaction of helium and hydrogen and other gases by using this method. So this is a very important experiment in your like UG, and as well as PG also we have this experiment. The entire process which I have explained to you is given in these points. You can go through each and every point now through the slides. Okay. So the gas under investigation is first compressed with the help of a compression pump, as I told you. Now the heat developed can be reduced by temperature of the water bath, which we have already talked. And finally the gas cools and the temperature falls. That's what we want to have, right? Then finally concluding this experiment, what are the main results? At sufficiently low temperatures, all gases show cooling effect by Joule-Thomson's effect. But at ordinary temperatures, students, this is an important point you have to remember. At ordinary temperatures, all gases undergo cooling effect under Joule-Kelvin effect, except two gases. What are those two gases? Hydrogen and helium. They show a little bit of heating effect. So when I just talk about helium, it shows about 0.014 Kelvin increase of the temperature. Okay. Next, the fall in temperature is always directly proportional to the pressure difference between the two sides of the porous plug. Then what is temperature of inversion? We can also learn this temperature of inversion by using this concept, Joule-Kelvin effect. Okay. See, below a certain temperature, by applying pressure, we achieve cooling. And that means cooling of gas means we get into liquid. So liquefaction of any gas can be done by this concept, by below the critical temperature. But what happens with some gases when you go on doing this process? That cooling effect decreases with the increase of initial temperature. So initial temperature of the gas, what you are taking is more, then obviously the temperature will be increasing. So instead of cooling, the concept of heating comes. Okay. So this temperature is called temperature of inversion. Okay. So every gas below its temperature of inversion will cool on passing through the porous plug. So this is what the conclusions made by Joule and Kelvin in their porous plug experiment. Okay. Now next, coming to the theory. So what all the things which we have talked is the entirely experimental procedure. So the scientists have given some theoretical expressions. What we discussed, high pressure will be denoted as P1, volume V1, temperature T1. In that way we will be designating them in some parameters and we will derive the equation. Okay, let us go into that. So the same concept which I have explained, the same thing is displayed on the screen now, students. That is the theory. So let P1, V1, T1 represents pressure, volume and temperature in the left hand side, that is the high pressure region, and P2, V2, V2 on the lower pressure side. And let U1 and U2 be the internal energies of unit mass of the gas before passing and after passing through the porous plug. So U1 will be the internal energy before passing through the porous plug, and after we can see as it as U2. So you all know what is the work done on the gas by the piston. So on the gas, the piston is moving from left hand side, right? So the pressure is building up. So what is the work done on the gas by the piston? By moving it, compressing it. So what is the work done? P1, V1. So PV is the work done. Now I am using them as P1 and V1 for left hand side. And the same thing, work done by the gas on the piston. So when you go to right hand side slowly from left hand side through the porous plug, you have P2, V2. Okay, there the work is done by the gas on the piston. Okay, now the net work done. What is the total work done? Net work done. So P2, V2 minus P1, V1. That is the net work done. So as the system is thermally isolated, I already told you, as madam already explained that it's a thermally isolated
different
system.
Types of
Among the different types of systems we talk about this thing. So isolated system. So what happens now? The expense of the rate of work done will be always equal to the change in internal energy of the system, because internal energy is only restricted to the system. It doesn't interact with the surroundings. So we have P2, V2 minus P1, V1 will be U1 minus U2, right? Next, by using those two equations, I just put the expressions this side and that side. So we get U1 plus P1, V1 is equal to U2 plus P2, V2. So in this way we achieve that U plus PV, this component is constant. Okay, U plus PV, the component of internal energy and work done, that is PV, will be constant. So what is that component designated as? Dani emani pilustam manam? U plus PV ni enthalpy. So that is designated as enthalpy. Okay, so in Joule-Kelvin effect, which property will be the constant? Enthalpy will be the constant. As you all know, for isothermal process, what will be constant? Temperature. In the same way, for adiabatic process, entropy will be the constant parameter. And now here in Joule-Kelvin effect, what will be constant? Enthalpy will be constant. So now we just go into the perfect gas. So for different gases, what is the expression for Joule-Kelvin effect? Now you go for a perfect gas. Here Boyle's law is obeyed. Boyle's law is pressure is inversely proportional to volume at a particular temperature of particular gas, right? So PV is equal to constant. So P1 V1 is equal to P2 V2, and hence obviously U1 is equal to U2. Now the Joule Kelvin effect is 0 for a perfect gas because there is no change in temperature happening for a perfect gas when it is made to pass through our porous plug. So there is no change in the temperature occurring for any kind of gas which is a perfect gas. So for Joule Kelvin effect becomes 0 for a perfect gas. Now when you come for real gases, we have three conditions. So we have below the boil temperature, above the boil temperature, and equal to the boil temperature, at the boil temperature. So below the boil temperature, P1 V1 will be less than P2 V2, hence U2 will be less than U1 because balancing the equation of enthalpy, because the entire enthalpy should be constant. But here P1 V1 is less than P2 V2, hence U2 should be less than U1. So hence the internal energy decreases, hence the temperature falls. So cooling effect is seen when the temperature, when the real gases undergo Joule Kelvin effect below the boil temperature, right? Now above the boil temperature, P1 V1 is greater than P2. That would be a vice versa for the previous one. This would be entirely reverse for the previous below the boil temperature condition. So here the heating effect occurs. Now at the boil temperature, P1 V1 will be equal to P2 V2, hence U1 will be equal to U2. Same as our real gas, perfect gas condition, when a real gas becomes a perfect gas at the boil temperature. So there will be no change in temperature, hence the Joule Kelvin effect will be 0. Okay students, clear? I hope I am very much clear on all the Joule Kelvin effect expressions and Thomson effect, right? Now the expression for Joule Thomson cooling we have. So we have to derive the expression for cooling. How much cooling it is possible? What is the change in temperature we are obtaining after passing the gas through the porous plug? So that is the final thing we have to achieve after doing all this process. So how do you do that? Again the network is P2 V2 minus P1 V1. Then the expression you can see here. So we consider it as a van der Waals gas equation. So where we have integral V1 to V2, the system is going to expand, like V1 is the volume at left hand side and right side it is V2. So integral V1 to V2 A by V square dV. So you know what is the integration of 1 by V square? It is minus 1 by V. So A by V1 minus A by V2, when I apply the limits V1 and V2 here, applying the limits upper limit and lower limit, I get the integration A by V1 minus A by V2. So the total work done is W is P2 V2 minus P1 V1 plus this one. This is the component which it is getting added up. That is A by V1 minus A by V2. If you remember, what is the net work done when I took simple medium without considering a van der Waals gas equation? We have P2 V2 minus P1 V1. ఇప్పుడు van der Waals gas equation తీసుకున్నాక అది యాడ్ చేసినాం. సో ఏ కాంపోనెంట్ యాడ్ అయింది? A by V1 minus A by V2 అనేది ఇక్కడ యాడ్ అయింది చూడండి ఈక్వేషన్ 1 లో. ఇప్పుడు we know that P plus A by V square into V minus B is equal to RB. So PV plus A by V, I am multiplying this V minus B component inside. So we get this expression. So finally when A by B are very small quantities, A and B are constants, right? V is the volume of the gas. So AB by V square can be neglected. So PV plus A by V minus PB is equal to RT. The same expression I have written here, excluding this AB by V square. Or we can do like this. We put PV on the left hand side and we took all the other things A by V minus P by V onto the right hand side. Next, P1 V1 is equal to RT minus A by V1 plus P1B. Similarly, P2 V2 will be RT minus A by V2 plus P2B. So I just subtracted them, P2 V2 minus P1 V1. We get this expression, equation 2. Now substituting this in net work done. What is the net work done? Students, that is equation 1 I told. So there I substitute this expression. So finally we arrive at this condition. W is equal to 2 into A by V1 minus A by V2 minus B into P1 minus P2. That is third equation. We have arrived at third equation. You know, again A by V1, A by V2 are very small. We can use the approximate relation like PV is equal to nRT. You know that ideal gas equation. So A by V1 is equal to P1A by RT. Again A by V2 P2A by RT, because I multiplied on both sides by A for this equation. Okay. Then we obtain this W expression as this way: P1 minus P2 into 2A by RT minus B. Okay. Now finally, what is Cp here? So when the system is thermally insulated, then the work is drawn from the internal energy. As I told again, the work is only drawn by the internal energy, because there is no chance of exchange of heat energy between system and surroundings for a isolated system. So only by change in internal energy only we can achieve the work done by the gas. Then what is the temperature fall? Minus dT, if I take it as fall, so it is minus dT. If Cp be the specific heat at constant pressure. What is specific heat? The amount of energy required to raise the temperature of a unit mass of substance by 1 degree centigrade. That is called specific heat. So specific heat at constant pressure. If this process this process occurs at constant pressure, then that specific heat is called as specific heat at constant pressure. Okay, that is designated as Cp. C a suffix P. So if Cp be the specific heat at constant pressure, then the amount of heat supplied to again restore the entire thing will be, what is that? Minus Cp dt calories. Okay. Now what is and in joules, minus Cp dt joule. Hence minus Cp dt joule is equal to, again I just substitute here, instead of W we are putting minus Cp dt. So Cp, it comes to the right side, cross multiply, I got dt is equal to this equation, fifth equation. Now from fifth equation we just come to three conclusions. So if 2A by RT minus B is positive, that is if T is less than 2A by RB, then dt will be negative, then the gas will be cooled. If 2A by RT minus B is negative, the opposite thing happens, the gas will be heated. And if 2A by RT is equal to B, there will be nothing in the system. That means there is no change in the temperature in the system. So cooling, heating, and there is no change in the system. So this temperature at which there is no change in the system is happening, the gas doesn't cool, what is, or neither cooling nor heating. Such process at what temperature does it happen? So that is inversion temperature, Ti is equal to 2A by RB. Okay, so this is the inversion temperature. So now I request our madam, Usha madam, like, is it okay for you?
Yeah, doing good explanation, Chandana. Next to go ahead. Now I have to take now I am welcoming in this discussion Dr. Varalakshmi madam. Can you we have so many wide range of applications in low temperature, so can you explain about these applications of low temperature, ma'am?
Yes, ma'am. First of all, let me thank you for giving me this opportunity, to you and Dr. B.R. Ambedkar Open University as well. As my colleague Chandana has already discussed, some of the applications of low temperature physics were already given. So apart from that, what are the regular applications and what are the other components are left out, I am going to discuss. So these are the objectives briefly. Thermodynamics of a refrigerator and the cycle of operation. Then what should be the definition of a refrigerator, and what is the effect of stratosphere while using the refrigerants, and effect of chlorofluorocarbons on the ozone layer, and what is Bose-Einstein condensate. Okay, these are the components we are broadly, and apart from that, there are certain broad applications apart from what Chandana madam has discussed earlier. So some of the applications are shown here. One is the cryogenic labs for biological and medical applications. As you all know, in every hospital we use liquid oxygen. So oxygen has to be, means oxygen cylinders will have oxygen in liquid form. So we have to reduce the temperature in order to liquefy the gas. That is one of the application. And then the another broad application is cryogenic calorimetric work to produce high standard of vacuum. The high standard of vacuum means the pressure should be around 10 to the power of minus 7 millimeters of mercury. And then the most well-known application was refrigeration and air condition. We use for domestic and industrial purposes as well. And finally, in the production of liquid hydrogen, liquid helium and oxygen that are used as fuel for the rockets as well in military and ballistic missiles. So this is how the refrigeration cycle operates generally. So we have 4 situations here. The first situation is we have 2 cylinders here, cylinder from system from A to B. In A to B, I don't know if it is visible for you students. You can see on the left side of the diagram there are 4 pictures. So in the first picture we have system from A to B. So here what is happening, the piston from the first cylinder is pushed inside and second cylinder piston is remaining constant. That means we are applying pressure on the first cylinder and there is no change in the pressure on the piston on the second cylinder. So here what is happening when some pressure is applied on the system? The temperature of the gas will slightly increase. That temperature, the excessive heat is rejected to a hot source here. Okay, so in the second case what is happening in the graph you can see from A to B there is a change, there is a decrease in volume of the system and there is an increase in pressure of the system. This is the curve. And then in the second thing, the volume, the pressure on the first cylinder is decreased as well as the second cylinder volume is increasing to the same extent. That means the volumes in both the cylinders are remaining as constant. Okay, this is the change from B to C. So in the graph also you can see from B to C there is no change in volume, but there is a drastic decrease in the pressure of the system. Okay, so in the third diagram we have from C to D. Okay, in the C to D, in the first cylinder there is no change in the pressure, whereas in the second cylinder piston is pulled in downward direction. That means we are increasing the volume of the system without any changing in the pressure. So here what is happening, inside there will be a change in temperature. The system practically cools down. Okay, and in the fourth diagram from D to A, here the first piston is pulled in downward direction, second piston is pushed in upward direction. The volume is remaining constant. So earlier whatever the excess heat it has received, that heat is rejected to the sink. This is the cycle of a refrigerator. How does it work? That means externally the refrigerant is going to expand, it is absorbing, that means internally inside the refrigerant is going to expand and absorbing the heat from the surroundings. After coming outside, again the compressor compresses the refrigerant and then the excess heat is rejected outside. That is how a regular refrigerator works. And in commercial refrigerant cycle it looks a little bit different. Okay, so the process is due to throttling. The process A is due to throttling. So here what is happening, from A to B there is a curved and dotted line. Throttling means, as explained by the Chandana madam, there is the gas is allowed to expand through a porous plug with a force. Okay, that is called throttling. So there is a decrease in temperature and pressure, and since it cannot be defined well, it is given with a dotted line from A to B. And the process from B to C is an isothermal and isobaric vaporization. Isothermal process is the process which is taken place at constant temperature, and isobaric process is the process which is taking place at constant pressure. So from B to C, if you observe in the graph, it is a straight line which is parallel to the x-axis. So here on the y-axis the pressure is constant. Okay, so only the volume is going to increase. And the process from C to D, if you see, this is an adiabatic compression to a temperature higher than that of the condenser. So there is a curved line which is a continuous from C to D, and if you observe, there is a decrease in volume and there is an increase in pressure. Okay, and the process from D to A is an isobaric condensation and cooling. If you see, this is also almost like a continuous line which is parallel to the x-axis, and the pressure is constant and volume is reducing. This is how the commercial refrigeration cycle is operated. And if you observe the efficiency because the efficiency of a heat engine, basically we know the refrigerator is defined as the Carnot engine which is operated in a reverse cycle. Okay, so if heat is extracted from a source at a higher temperature and this is rejected to a sink at a lower temperature, the difference between the quantity of heat absorbed and quantity of heat rejected is utilized in the form of work done by a heat engine. That is how a normal Carnot engine operates. But this is a reverse Carnot engine where heat is extracted from the sink which is at a lower temperature and is rejected to the source which is at a higher temperature. So external work is done on this Carnot engine in order to get a cooling effect. So since it is a Carnot engine, the efficiency is defined like this. It is the ratio of heat extracted from the cold reservoir by the work done by the refrigerant. So eta is the efficiency which is equal to QL by W. QL is the quantity of heat extracted from at a low temperature, and W is the difference between QH and QL. QH is a quantity of heat extracted rejected to the high temperature, and QL is the quantity of heat extracted from the low temperature. And then we have another type of refrigeration that is called vapor compressor type of a refrigerator. So here we have, there are two valves V1 and V2 on the diagram at the pump P. Okay, the pump P is connected to both the valves V1 and V2, and V1 is connected to the right side part of the system. This is called the evaporator, and V2 is connected to the left side of the part which is called the condenser. Okay, so basically what is happening when the valve V1 is only this is used to suck for the suction of the low pressure vapor from the evaporator, and the valve V2 is for the discharge of compressed vapor into the condenser C. Okay, the condenser is cooled by circulating cold water, and the vapor liquefies due to high pressure and lowering the temperature. So the liquid refrigerant passes through the throttling expansion needle valve or the regulator valve which is shown at N in the picture. So due to the low pressure, the liquid evaporates into the evaporator E, extracting its latent heat from the cold storage space surrounding E. The low pressure vapor is sucked in again by the compressor to continue the operation again and again. So this is done with the several cycles. Always heat is absorbed at the evaporator and heat is rejected at the condenser. Okay, so like that the refrigeration process will carry on. So what should be the characteristics of the refrigerant what we are using? Okay, the latent heat of vaporization should be very large. As you all know, latent heat is the quantity of heat absorbed by a substance only to change the state from either from solid to liquid or liquid to vapor without any change in its temperature. So latent heat of vaporization means the quantity of heat absorbed by unit mass of substance to change its state from liquid to vapor without any change in its temperature. That means practically the substance will be at its boiling point. The second condition is the refrigerant should be vapor at NTP. NTP means normal temperature and pressure, but should easily be liquefied when compressed and cooled. The third characteristic is the pressure on the refrigerant in the evaporator should be higher than the atmospheric pressure at minus 15 degrees centigrade, so that the impurities of air should not block the passage. Then the pressure of the refrigerant in the condenser section should be moderate, so that there shall be no leakage. The specific volume of the vapor of refrigerant should be small in order to have the condenser size small. And mostly used refrigerants are ammonia, sulfur dioxide, and chlorofluorocarbon. This is called chlorofluoromethane. You know, methane means CH4 instead of 4 hydrogens. 2 chlorines and 2 fluorines are substituted. The common usual name for this is freon. These are the regularly mostly used refrigerants. Then what should be the effect of chlorofluorocarbons on stratosphere zone? What is the stratosphere? Here is a brief introduction about the layers of Earth's atmosphere. So we know we have a thick blanket of air around the Earth. So up to 12 kilometers from the surface of the Earth, whatever the layer is there, this is called troposphere. And the temperature of the troposphere is from 15 degrees centigrade to minus 50 degrees centigrade, and the gases present in this troposphere are nitrogen, oxygen, hydrogen, carbon dioxide and ozone. Okay, and then after troposphere, from 13 kilometers to 50 kilometers range, we have stratosphere, and the temperature of the stratosphere is 0 degrees centigrade to minus 60 degrees centigrade. So here ozone is the chief ingredient along with the other gases, but with a low density. Then above this we have mesosphere at an altitude ranging from 50 to 85 kilometers, and the temperature ranges from 0 degrees centigrade to minus 85 degrees centigrade, and oxygen and nitrogen oxide gases will be present in this. And above this there is a thermosphere ranging from 85 kilometers to 800 kilometers range temperatures, and are unpredictable because the temperature sometimes though they may go very high values also, and the gases present will be oxygen and nascent oxygen and nitrogen oxide, but these gases concentration will be very, very low. So what is the importance of ozone layer that is present in the stratosphere? So 90% of the stratosphere is almost filled with ozone. The absorption spectrum of ozone shows that it almost absorbs all the radiation of wavelengths less than 3000 angstrom units from the sunlight. This layer absorbs the harmful ultraviolet, X-rays and gamma rays. This helps the biological sustainability on the Earth. As you know, in an electromagnetic spectrum, the visible radiation is ranging from 4000 to 7500 angstrom units. So at the 4000 angstrom units we have violet, and at 7500 we have red. So from violet to red, if you observe the frequency decreases. So the energy of radiation is directly proportional to the frequency. So violet is violet rays will have more energy when compared with the red color. So below violet, what all are there? They are ultraviolet, X-rays and gamma radiations. So all these are very powerful radiations, highly energetic radiations, and they are harmful for the living things that are present on the Earth. So ozone layer is practically filtering all these radiations. So the harmful effects of high energy radiation are explained here. The ultraviolet radiation rays damage the deoxyribonucleic acid, we call DNA, associated with basic life form. Ultraviolet harms the reproductive molecules of all the living beings. Ultraviolet rays exposure increases the occurrence of human skin cancer, and ultraviolet exposure reduces the rate and efficiency of photosynthesis, and UV rays affect the climate of our Earth and hence cause global warming. So how does this ozone, what is meant by the depletion of ozone layer, and what does the refrigerants they have a role to play? So global warming is associated with holes in ozone layer of our atmosphere. The holes are mainly due to industrialization of developed countries and leakage of CFC. CFC means chlorofluorocarbons and various derivatives. The holes make Earth exposed to the ultraviolet radiation. Holes are near North Pole of the Earth and at Antarctica. The ice at that place melt unnaturally. The water level in seas around the world is rising. Hence, coastal regions of Earth they are in danger of inundation. So, the effects of chlorofluorocarbons on ozone layer. As we know, ammonia and sulfur dioxide were the refrigerants in the earlier parts of 20th century, that is in the year 1928 until the invention of CFCs. The evaporation of CFC is around minus 23 degrees centigrade. So, the efficiency of chlorofluorocarbons is around 60%, which is more than the earlier refrigerants. That means earlier the ammonia and sulfur dioxide, their efficiency used to be 45%, but the efficiency of CFCs is 60%. That's why this is the most sought refrigerant industrially. And CFCs have good conversion from liquid to gas and then back from gas to liquid also. These substances are also used as solvents in electronics industry. CFCs are used as foam blowing agents in fire extinguishers. They are propellants in aerosol industry in for asthma patients. Along with freon, carbon tetrachloride and along with freon, we have halogens and some carbon tetrachloride or some of the gases, they leak into the atmosphere and they cause danger to the layer, ozone layer. Such materials are called ozone depleting substances, ODS. Okay, so 26% of ODS, ozone depleting substances, are used as refrigerants. 25% of ODS are used as foam blowing agents in fire extinguishers. 26% are used in aerosols as solvents, and the remaining 7% are used in other applications. The ultraviolet radiation falling on CCIF release chlorine. So, chlorofluorocarbons, they are releasing chlorine. The chlorine atom reacts with the ozone, produces ClO and oxygen molecule. The reaction is given below. CCl2F2, upon exposure with the ultraviolet radiation, it is releasing single chlorine atom. This chlorine atom will react with ozone and it is making the products as ClO plus oxygen. So, once the chlorine atom, a single chlorine atom is formed, it is left in the atmosphere, it survives for a very long time, that is from 20 to 100 years. So, if a single chlorine atom is remaining in ozone molecule, this has ability to break the ozone. So, in 1990, 1000 tons of ozone depleting products were identified on the earth. A big hole like thing was observed at Antarctica region and in the layers of ozone. So, this made governments of all the countries in the world to be alert in this matter and take decisions to stop reducing ODS materials, ozone depleting substance materials. By 2010, the ODS materials are found to be 50 tons. So, there is a notable reduction of this ozone depleting materials. Okay, and there is a Bose-Einstein condensate. So, this is another form of matter. So, Bose-Einstein condensate is a new state of matter essentially associated with a very low temperatures of about 1 milli or micro degree Kelvin. So, Bose-Einstein condensate substances is associated with particles of positive integral spin and which are called bosons. So, here we have all the fundamental particles divided into two categories. They are fermions and bosons depending upon their spin. So, bosons are the particles which are called which are having integral spins like 0, 1, 2, 3, etc. And fermions are the fundamental particles with half integral spins like 1 by 2, 3 by 2, 5 by 2, etc. So, the net spin of 2 electrons, if 2 electrons are joined and spinning, it can be either 0 or 1. Hence, this situation leads us that it behaves like a boson, that means a combination of 2 electrons. According to Pauli's exclusion principle, no 2 electrons or fermions will have all the set of 4 quantum numbers same. or same energy. But in case of bosons, photons are also bosons. There is no limit in their number and with the same amount of energy. So with a particular wavelength, a large number of bosons can exist. So ultra cold atom groups together are called as if they are one single super atom. This displays distinct quantum properties. This leads ultra cold atoms are to be used for quantum computation and quantum simulation. So superfluids will improve the performance of atomic clocks, integrated circuits and high precision gyroscopes. So I hope, madam, within the time given, I think we could cover a few.
Yeah. Thank you, ma'am. Thank you, Chandana madam. Can you little brief explanation of Kapitza method?
Yes, ma'am. We'll look into that. Thank you.
Just wait meanwhile.
As we have already discussed the 4 different kinds of methods to achieve low temperatures in materials, especially gases, we have read about. I just explained around 2 methods. When coming to the Kapitza method, it's a specific method in which we have attained the low temperatures of liquid helium. Like helium can be liquefied by using the Kapitza method. So when we just look at the equipment and the apparatus which we have designed for the Kapitza method. So there we pass on the helium which is in a dry state with a pressure at 30 atmosphere through a condenser,
Brief discussion.
through a compressor, and then finally we will go to the water bath. So the temperature of the gas will be reduced when it is passed through the water bath, W. Then we will pass the gas through liquid nitrogen. Liquid nitrogen. Here. So now you can see the students. Now you can see the Kapitza liquefier on the screen. So the helium, which is a gas at 30 atmospheric pressure, which is in dry state, is passed through the liquid, passed through this piston, and the compressor is there here with P as a piston here. Now the compressed gas is passed through the water because as I already told you, the compression increases the temperature of the gas. Then while the gas is passed through the water, the increased temperature will be again coming into the back, the reduced temperature. Now that gas is passed through the liquid nitrogen bath, which is at minus 208 degrees centigrade. Now here at this point A, the gas gets splitted into 2 parts. Okay, one part that is passed through the heat exchanger here, and the other part will be passed through the expansion engine, right? Okay. That expansion engine works under adiabatic process, adiabatic expansion. So here in adiabatic expansion, the gas reaches to minus 263 degrees centigrade. That's a very good lowest temperature we can achieve using this Kapitza method. Yeah. Now this 263 degrees centigrade gas will be passed, and again we will reach at minus 268 degrees centigrade. So this is the method, madam. We can obtain the liquid helium.
Thank you, Chandana. Thank you. As we conclude these teleconference sessions, thank you very much on low temperature and applications of low temperature. First of all, I would express my gratitude to our experts, Chandana ma'am and Varalakshmi madam, for sharing their knowledge. Chandana madam and Varalakshmi once again.
Okay.
Thank you very much.
Thank you so much.
Thank you so much. Thank you.